Hello Finxters. Today we'll cover a topic of breadth-first search algorithm. So, how it goes. First of all, I'm going to tell you a little story about our reality. This is actually an intro to follow up with the breadth-first algorithm later. So, our reality is, as you may imagine, a very diverse, complex system, and in many cases we would ask ourselves how to get a specific information from it. So, to be able to get any information from a complex system, we have to make a specific abstraction of it. So, in our sense, this abstraction focuses on what's important. It actually simplifies the reality. And in our case, we would like to focus on reality's members and relationships. So, in the previous picture, we can see that there are many of members. Some of them are acquaintances, some of them don't know each other, but there probably is a way to get from person A to person D through some common acquaintances. So, as we defined, we have abstracted the members and the relationships, and how to represent them in a more formal way to be able to extract any kind of information we might find interesting. One of the best ways to do so is by introducing a graph. So a graph is a structure where members are also named vertices. One member of this set of vertices is a vertex. We call it a vertex. And these relationships between members are called edges. So what does it mean? It means that if we focus on vertex number 1, let's say this is a person, and its immediate acquaintances or friends or relatives are, oh, actually it has only one friend, and it's a vertex number 0. So 0 seems to be more sociable. It has even 3 friends. His friends are vertex number 4, number 5, and number 2. So to simplify, a graph is a structure which has only 2 components. It has a set of vertices and a collection of edges. So in the next step, this is actually the right time to ask ourselves, now that we have this graph which we use to represent a simplified version of reality, how can we find any information from it? Actually, some of the questions we might ask ourselves are, is this information even available? How far is it? How to get from point A to point D? And where to even start? Considering the graph, a starting point is a completely arbitrary choice, but it is usually conditioned by some, let's say, natural conditions. In my case, if I would ask myself how to get to some person I don't know, I would try to remember who is in my immediate network of familiar people who might know the other one, and so on and so on, and I would somehow think about a way to reach someone and to ask him something, let's say, in a way. So how can we get this in a more formal way, given that we know about this whole network, that we have described it by using a graph? So here is one of the answers. It's a breadth-first search algorithm. This algorithm actually works by, at least in our example, it's not any different in the real world. It works by defining a starting vertex. In this example, I've chosen a vertex number 5, and I'm asking myself, according to these questions, is this entity, like a real world entity, number 5, is it available anywhere in the graph? How far is it? How to get there? And we actually have this answer to the 4th question, where to even start, because I've designated the vertex number 5 to begin with. So we are looking for an entity number 6. Currently our viewpoint is focused on the vertex number 5, and the way to do it is by taking each vertex like this, marking it as visited. This is an important step because we don't want to visit the same nodes over and over again, the same vertices. And in that sense, once we have placed this vertex number 5 on our queue list, the next step to do is to explore its immediate neighbors. So remember what I was talking a moment before. You are asking yourself who is it that you know, who is in your immediate network. For example, we were talking about a network of acquaintances, but it can also be a network of cities or something else. So to get back to our example, we have marked this vertex number 5 for exploration, for discovery, and now that we have done so, consider this to be a level 0 search. A level 0 search always starts at this arbitrary root vertex. So in the next step, we will explore the vertex number 5. We have discovered that its adjoining or neighboring vertices are vertex 0 and vertex 3. We have nothing to do with vertex number 5 anymore, but now we would like to know who is in the immediate neighborhood of vertices 0 and 3. So now that we know about them, they are placed on our queue, and we are going one step further, and we will explore them, and they were in level 2. Excuse me, vertex number 5 was in level 0 search, vertices number 0 and 3 were in level 1 search, and here in level 2 search we have vertices 1, 4 and 2. You can see that they are immediate neighbors of our vertex 0. The same as with vertex number 3, it shares this vertex number 4 with vertex number 0, but it doesn't matter. Regardless of which one vertex 3 or 0 gets explored first, it will visit this vertex number 4 and put it in the queue. Oh, sorry. So in the next level, we are going to explore vertices 4, 1 and 2. And by doing that, we have discovered and actually visited this vertex number 6. Remember, in the beginning we were actually looking for the entity number 6. So in the following step we can decide, as actually we were doing through each step, is this entity we were looking for one of the vertices we have already visited and explored. In our case, this vertex number 6 is found right now. So when we marked it as explored, it gets recognized as the solution, as the entity we were looking for, and the algorithm constructs the path that led to it backwards. And now we can see that since we started from this vertex number 5, our actually shortest path leading to a vertex number 6 is 5, then through its neighboring edge through the vertex 0, again through its neighboring edge to the vertex 2, and finally through its neighboring edge to the vertex 6. So our path is 5, 0, 2 and 6, and our vertex, our entity we were looking for in the beginning, is finally found. So this is how the algorithm works. I'll repeat it once again, but in shorter steps. We start by choosing an arbitrary vertex number 5. We look for its neighboring vertices. These are 0 and 3. in level 1 search. In level 2 search, we will look for their neighboring vertices. These are, as you will see, 2, 1, and 4. Same goes for vertex number 3. It also has this vertex number 4 as its neighbor. We still haven't found our entity, and we still have these marked vertices to go, so we will search further. And in the next step, we have marked them as visited first, and they are visited when they are light blue, and they are explored when they are dark blue color. And in the following step, we will take this vertex number 2, marked it as visited, and now that we have also found in this last level this vertex number 6 as visited, when we explore it, we will find that it is our solution, and here we go, here we have a full path. So I wanted to show you first how to use graphs to abstract some kind of a reality. Is it a social network? Is it a network of is it a like internet network, or a computer network, or a network of production steps in a factory, or anything else that can be recognized as having members and relationships? When formalized to a graph, it is formalized to vertices and edges. And once you have this kind of a graph, you can use, for instance, in our today's topic, you can use a breadth-first search algorithm to actually find the entity of interest, and to discover what is the shortest possible path to go from the starting vertex to this entity, to this ending vertex that you are looking to find, if there is any in the graph. If there isn't, then of course you wouldn't find it. Perhaps a few more words on graphs alone, although you can find all about it in the written part, in the article. The graph has elements, has its vertices, but not every vertex has to be connected to another. In this graph, for instance, we have 3 unconnected vertices, and as such they are unreachable. You can also have limitations to go only in one direction on the graph, so in that case you cannot connect the graph in each direction. Actually, you cannot traverse it any way you like. So for instance, if let me see which one is the best suited for a view. For instance, if this vertex number 2 can only go to number 0, but not from 0 to 2, we would never find this vertex number 6, because we would be banned from even going in this direction from 0 to 2. So in this case, where we have unidirectional graph, we can go anywhere we want, but in a case where you have a designated direction of traversing, you have some other limitations which you must also take into account when implementing your algorithm and when doing a traversal or walking around the graph, so to say. So this is it for today. Thank you very much, and I hope you managed to learn something new and interesting. And until next time, bye bye.